So good afternoon, everyone. How are you guys doing today? It's Fred. So it's good to be back here at Flink Forward and back in Berlin again. This is my third visit to Berlin just in 2018. And this is my fourth successive Flink Forward in Berlin that I'm attending. So on that note, just a brief introduction. Joey, you want to go over?
Yeah, so I mean, as mentioned, me and Suneel are both Apache Software Foundation members. That's sort of, we're here in that capacity. I'm a committer on the Apache NiFi project and PMC member on Streams, which is, oriented around social media streaming and activity streams. Suneel as well is a PMC member on that project, among some others that are probably more well-known.
And a side note about myself, I'm very popular with the taxi guys in Berlin. They know me very well now. So the agenda for today's talk, how many of you guys have to deal with the large corpus of text, large text corpora, document corpora, ResearchGate obviously, and yeah. And how often do you have to do topic modeling as to see what's going on in the documents? What is it that you're saying? It's very often, right? Okay, so what is the motivation for topic modeling? What are the existing approaches that we have today for topic modeling? And let's say if we have a stream of data coming in, it could be a Twitter stream or a social media stream. How do you do topic modeling on streams as opposed to a batch? So that's what we'll be looking at today. And this is a research thing that we just kind of worked on the side and using Flink and stateful stream processing in Flink. And we were just trying to see, how can we build some kind of a lambda recap architecture for actually doing real-time topic modeling, learning, and inference. Inference, yes, you can do that in streaming, but how about the learning process itself? Yeah. So on that note, so what are topic models? Obviously, folks who are doing topic modeling and working with text collections, they should know this. So basically, you're trying to discover the main topics in huge collections of documents. And let's say if I have a big corpus of collection of documents, what are the main themes that are being discussed across all the documents? Or let's say it could be a social media stream. What are the main things that are being discussed in the social media feed? And if you're looking at research papers like Archive or ResearchGate, what are the topics that are kind of recurring across different papers that are being published? So those are the kind of things you want to look at. And this could be across a large, what you saw here is across a complete corpus of documents. But if you're looking at a specific document, individual document itself, you want to see it's kind of arranged in a different paragraphs. You have different structure. You have a document structure, and you have all the paragraphs. And you want to see what are the main topics covered across a document, across the different sections. And what is the most distinctive topic? You can come up with a bunch of topics, but which is the most distinctive one from all the collections that you have come up with that you want to identify? So how do you use these topic models? So let's say you create your topic models and you have your topic models. How do you use that? So most search engines, they use topic models for text summarization and for organizing text into collections based on the topics. And you can also annotate your documents with the topics that you have discovered across the corpus, right? And sometimes you want to see what are the hidden topical patterns across a big collection of documents that you want to uncover. So on that note, what are the most common approaches that we have today for topic modeling? So obviously, the first one is LDA, latent Dirichlet allocation. I'm not going to go in-depth as to what latent, Dirichlet, and allocation, each of those mean. So I think it's kind of not relevant to the context here. And I don't want to freak you guys out with the math. So in the LDA, basically, you're trying to compose topics by the probability distribution of a bag of words over a bag of words. And the documents are kind of composed by the probability distribution of the topics. So the topics are composed by distribution of words across all the documents, and the documents are composed by distribution of topics across all the documents. And this is a purely batch-oriented algorithm, the way it's done. So if you look at the old Mahout implementation of LDA, it's on MapReduce. It's a batch-oriented process. And anytime you add a new document, you've got to run the whole batch all over again on the entire corpus. So yeah, this is a plate diagram for what an LDA model looks like. So in a nutshell, documents are a mixture of topics, and topics are a mixture of words. So documents can be generated by drawing a sample of topics and then drawing a sample of words. So if you look at this plate diagram here, alpha and beta are your priors. And initially, when you start your LDA training process, you choose alpha and beta from a uniform distribution. which could be between 0 and 1, any value between 0 and 1. And then theta is the per document topic distribution. So in a document, how many different topics can you uncover that's what theta gives you here. And the phi is for each topic, how many words across all the documents belong to a specific topic. So it's a kind of a probability distribution that you're looking at. So any questions on this slide, or is it, do you want me to explain more on this? Okay. So the other approach after LDA is something called latent semantic analysis, which was used in the search engines in the early days. So basically, you have the entire collection of documents, and you create a TF-IDF of every word that you see across the documents. So you have a document and the term matrix. It's a document and term matrix. And you want to reduce that matrix using a singular value decomposition, SVD. And then you take that matrix for computing the topics. So this, since you're doing a singular value decomposition, it's again a batch process. It's a batch-oriented process. So yeah, this is the traditional way of doing topic modeling. So obviously, this old-fashioned way of doing topic modeling, they had some drawbacks. Number one, someone has to manually label all the topics. So somebody has got to come up with labeling the topics is a manual task. For example, let's say if I'm doing an LDA on some documents and I come up with 30% basket and 15% ball and 10% this guy's drunk. So, well, the topic for that document could be basket or ball or drunk, but it could as well be basketball. It could be a basketball document, right? So yeah, so you got to manually label the topics. So yeah, the other common approach is, yes, deep learning, of course. If you don't say deep learning today, nobody listens to you. So yeah, that's a hard fact. So you can do a supervised LDA using a deep neural networks, and obviously the inference, there is a speed up in the inference. Of course, the training is slow, as with any deep learning models. And they have deep belief networks now for topic modeling, which all of these are again batch oriented. So when you talk about documents, and Google came up with something called word2vec back in the day, and embeddings, the whole concept of embeddings. So you can take a bunch of words and embed those words in a vector space. And words that are very similar, like king plus man plus woman minus king equal to queen. So man and woman are very close together in a vector space. Similarly, you can take an entire document and project that document onto your vector space, which is it's called an embedding. And so basically, semantically similar documents, they kind of fall into the same, very close to each other, and they're very close to each other in the vector space. And how do you learn these representations? And for word2vec and all of these, they use a shallow neural network for doing that, learning word2vecs, and basically for learning embeddings. So on that note, for topic modeling, the Stitch Fix had come up with something called LDAcubic, which is using embeddings for computing an LDA. And so they're using basically an LDA and word2vec, kind of mix them together to create something called LDAcubic. And now you can do anything to vec. So you can take whatever data you have. If you have customer data, customer to vec, and you can compute which customers are similar and which two customers are screwing up each other. Okay. So, and how do you navigate these embeddings? So here in this diagram here, this is an example of a master, student, teacher, and student and teacher are closer together in space, classroom, teaching, curriculum, instruction. So similar words kind of, come closer together in a similar space region. And so you kind of have a geometric navigation. So from this word to this word, what is the distance? And which is the closest word? You come up with the closest words for a specific word. So the other thing that comes up when you're dealing with the document, large collection of documents, is static versus dynamic text. So obviously, learning topic models has always been done over a fixed collection of documents. And the way you do that is you go get the document collection first, you train a model and you fit the model to the documents, and then you extract the topics, and then take those topics into whatever downstream tasks you have. But in real life, documents are not fixed. And if you're dealing with social media, it's a complete stream of data that's coming in every minute. And it could well happen that you don't have a document collection to start with, so you have a cold start problem. And obviously, if you're dealing with large collections of documents, you're obviously going to hit the memory limits, trying to train that. And if I add a new set of documents, so if ResearchGate has X number of papers and 10 papers get published tomorrow, you got to take the entire X plus 10 number of papers and reprocess the whole thing and retrain your whole thing. So in today's world, it's all dynamic data, stream, 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 Twitter stream, Reddit stream, or whatever streams, papers on ResearchGate and Archive that are getting published every day. So how do you deal with topic modeling on streams? And so that's what we kind of started off with as a research project. So questions for you guys. How many of you guys are doing inference or scoring on streaming data right now for topic modeling? Okay. And how many of you guys are doing online learning or optimization on streaming data? 1, 2, okay. So the second one is hard because the algorithms don't exist for most of the tasks. They have very few algorithms which can do a very limited set of stuff. But also because people don't know that there are some algorithms that can do that. So it's kind of in the research and academia, but not into the industry, never made it to the industry. So on that note, we are going to talk about topic modeling on streams. How do you do topic modeling on streams? So today, me and Joey are going to talk about 2 approaches. So as a use case here, we took the entire JIRA for Flink, Apache Flink JIRA, all the issues. We ran that through a Flink pipeline, calculating the embeddings, extracting the paragraphs for each JIRA, getting the embeddings, and then trying to calculate the topics for each JIRA item. Okay, I cannot do a live demo of that because it takes forever to run, and I was running it offline. Okay, and Joey is going to talk about online LDA implementation. How do you implement an online LDA algorithm that's Stanford? Yeah. Yes, some guy wrote an online LDA algorithm paper, and how do you implement that using Flink stateful stream processing? So let's look at learning topics on JIRA issues. Okay. So this is the complete workflow, and I'll just show you some of the code with the complete pipeline. So you have your JIRA. You take your JIRA text for Apache Flink, you get all the JIRAs as a stream input data source. The second thing you do is you detect the sentences. So for detecting sentences, we are using Apache OpenNLP sentence detection model for English. And once you detect the sentence, the next step is to tokenize. So this is a standard NLP pipeline. So you detect your sentences, then you tokenize that, then you compute something called part of speech tagging, and then you do something called chunking. So this might be obvious to most of you guys. So part of speech tagging. So what is part of speech tagging? Basically, you take each token and you say it's a noun or a noun phrase, or it's a verb or a preposition or whatever part of speech it is. And then you take that as input to the next step, chunk. So what is chunking? Chunking is basically you take all those individual tokens along with their part of speech tags, and then you try to create phrases out of those tokens. So this Kerberos, yarn, Kubernetes could be a phrase that you create from chunks. So you take those chunks, you take those phrases from the chunking step, and then you create a vector representation of that, okay? And then you take that vector representation, and so there are 2 scenarios. You're working on a stream of data, and we create windows on the stream of data. So you have a window has, let's say, a size of 100 JIRAs in window 1. So initially, we have the cold start problem. How do you deal with the cold start problem here? So let's assume that your priors are 0.5 and 0.5. And then you create the embeddings for the first window of first window. And then you take those embeddings, put that in state, in a value state, in Flink. And then the next window comes in. So you take that next window, compute the embeddings, and take the embeddings from the value state, the previous state, take the both of them, average them together, and take that average value. From the average value, you get your topics. What the averaging does is it creates it averages the vector space for both the representations and puts that it's a paragraph vector, and represents that in point space. So, and from that, you get your topics. The topics could be, for this example, what we did is, during the chunks, you get a lot of noun phrases, verb phrases, and it could be different phrases. We filtered out all those we only filtered out for the noun phrases. We only take the noun phrases. And from the noun phrases, we are creating the embeddings for this. So the next window comes in. So you have your topic model in state now. The next window comes in. It creates its new embeddings with noun phrases. You take the topic model that's in state here, and you take the new embeddings. You take both of them, calculate the average, and update your state. Okay? So that's your training process right there. That's how the training is going. Now, let's say you're doing inference. So this is the inference pipeline here. So the inference pipeline, he goes to state, reads the model, and then calculates the topics. figures out what the topics are. So this is the training phase here, and this phase here is the inference phase. So the entire thing is running in a Flink pipeline. So let me switch to the code to see how this works. Okay, here. So let's see, view presentation mode. Okay. Okay. Sorry. So this is your input stream with the JIRAs. Okay. So the first step is what we saw in the workflow. You do the tokenization, then the part of speech tagging, and then the chunk. So on the chunks, you get once you get the chunks, you create a window of 100 elements, and then you calculate the embeddings for those 100 elements. Okay, and then you calculate the embeddings again for the next window of 100 elements. Then you, for the two successive windows, you calculate the average embeddings, and then you create a topic model from that. So that's the complete pipeline. And you write it to wherever. It could be to writing to a sink or wherever you want to write that. It could be to in memory. So this is how it actually works right now. So this is the training process, and inference would be just calling the topic model itself right away. Okay, switch back. So any questions on this so far? So this is, again, just to reiterate, this is the training process, and this is the inference process, all happening in kind of like is it a lambda or a kappa? I have no idea. They don't make sense to me anymore. So anyway, so yeah, in Flink kind of, obfuscates all that, and Flink, you can pretty much do training and inference on the same workflow. So anyway, so here's an example. So we ran this for the entire JIRAs on the Flink JIRAs in Apache. And so let's say this is a Flink issue number Flink 9963. And this is the description that you saw in the JIRA. And further down, you also see comments by the different people participating in the JIRA. So we took all of this text, and we tried to calculate what the topics are. So for example, for Flink 9963, the topics we came up with is format factory, table schema, table sync, sync factory, source, table source. And if you look at the JIRA description, sometimes it might be useful to just read or write a single value into Kafka. We should add a single value serialization schema factory and a single value deserialization schema factory for the numeric types. And there's further discussion further down in the JIRA. So yeah, so these are the topics we came up with for this particular Flink JIRA. So let's look at the next JIRA, Flip6. Yeah, Flip6. So fix Flink yarn Kerberos integration for Flip6. Okay, and this JIRA has a big discussion thread going, across several other JIRAs. So if you go further down, there's a big discussion thread, even though the description is nothing here. So we ignored the description and we went further down to actually mind the discussions. And the topics we came up with are yarn Kerberos integration, and yarn Kerberos. So these are the different non-phrases that we came up with from this. Okay. So any questions so far on this? We are not, but actually we should do that. And we are not right now. We are just looking at each JIRA individually. So, but yeah, that's when we looked at Flip6. Yeah, I think we should have done that, looking at the related tickets. Yeah. Okay, with that, I'll hand over to Joey to talk about online LDA and how to do Bayesian inference.
Yeah, so this is going to be the more conceptual piece of the talk, but the goal is to sort of convince you that we should always be thinking about streaming and online algorithms first, and because in many cases they are available, and in many cases they're actually not more difficult. So to sort of start things off, so the LDA model, it's a probabilistic model, and so what you really want to do is be able to calculate the posterior distribution from the way that you break down the the joint distribution. So when we looked at that so-called plate diagram that was telling us what the parts were in that model. And so really what we want to do is figure out how, on the basis of the data and our priors, what the actual distribution should look like. When topic models sort of got their start, when LDA was first discovered or formulated, it was done using Monte Carlo methods. What that essentially means is you're going to repeatedly sample from conditional distributions until you hit some stationary point. It's essentially a batch process. So people then noticed that there's an alternative where instead of sampling and estimating the posterior distribution, so you can sort of set things up if you have an auxiliary function where you can actually do an optimization and do that optimization on that approximation to the function that you actually really want. And that's something called variational Bayes. And so that's what we're going to be looking at with online LDA. So what's nice about it is that it sort of, it has it sort of looks like an EM-like optimization, so it's pretty straightforward to do. It's often faster and more accurate than doing, something with MCMC, and most often it's easy to come up with a way of doing it, online or iteratively. So we can do this with streams. That's sort of the punchline of why, this is worth looking at. So online LDA is, one approach to using variational Bayes to, fit topic models. It can be done batch or online. So as we know, there's sort of this convergence of, batch and stream. So your batch is going to be your entire stream. Online LDA sort of, works the same way. And you're going to be iterating back and forth, between optimizing, the topics and, the per word topics and the per document topics. And this is actually turned into the default, approach for doing, topic optimization in most packages. But what's interesting is that they didn't really do it for streaming. They did it because you then don't have to keep all of your data in memory, and you can just take, small batches and, roll those in. So, you'll see this in GenSim, scikit-learn, MLlib. So if we look at what it is, so this is going to be a little bit dense, but what I really want to sort of break things down into is if we're going to think about doing streaming, we have to figure out, which things are basically going to be constant, which things are going to be, at a task level that we can basically throw away at some point, and which things do we have to think about in terms of state. So when we're looking at this lambda thing is the thing that we really want, to get out of here. So that's going to be the ultimate goal, and we're going to have to keep track of that. So that's really the thing that's going to require state. So things like priors and things and learning rate, decay rate, stuff like that, that's just going to be constant. So, we can just specify that in the job and don't have to worry about it again. And then things that are batch local, those will be used when the calculations are being done to do the update into Lambda, but we really don't have to worry about those outside of an individual task. So the hard thing then is in a stream processing system, how do we keep track of Lambda? And so how do we represent that piece? So let's then just map this onto what this looks like in Flink. So we can set, global job parameters. We can pass things as, arguments to an operator. Really easy. The stuff that's mini batch local, that's trivial as well. So that's going to be in an individual task or an individual operator. So we actually don't have to worry about it much. So then the job global stuff is where we have to do some thinking. Probably the easiest thing to do is to use an external key value store. And this isn't a problem because your topic matrix, in most cases, isn't going to be obscenely large. So you see things on the order of thousands or tens of thousands of vocabulary because it's going to trail off into stuff that doesn't matter. and anywhere between dozens to 100 or so topics. That stuff's easy to store somewhere. So it'd be easy to do in a key value store. We could do this using accumulators. So if we go back and look at this, so this is the thing that we're ultimately going to want to do. The one with the tilde is going to be a local calculation, and we're using that to update the global one. And so we're really taking a mixture of what the overall, basically what the what we thought it was prior to starting this, plus some update. So we can often just look at these as increments. So you can do a variant of this. So this particular model actually doesn't specifically say, hey, I can just do this with increments. But if you want to do something dirty, you can get good results generally doing this kind of thing. If you say, instead of doing probabilities here, we're just going to convert those to counts, and then it's a little bit easier. And then the the mini batch or the batch size, we can just determine those by windows. So there's probably a way to do this with broadcast state. So that's going to be a little bit more difficult to go about it, because if we think it through, we're going to have what amounts to this a stream that has this lambda that has the overall topics, and we're going to have to be updating that thing. So it's not as simple as connecting the streams and just using it over and over again. At each iteration, we're actually going to have to change that. Okay, so what? Why do we care? So, Suneel already mentioned that one reason we care is that corpora actually aren't static. Streaming data is pretty pervasive at this point. What I'd say is that there's really a more general thing that you should be thinking about here. For a lot of tasks, and this is sort of across the machine learning space, people just do batch training and optimization, even if there's good algorithms for doing it online. So it's a little bit, it's not perplexing as to why this is the case. The field just sort of grew up on, smaller data sets, and they get progressively larger, and, there's more streaming data now. So, really, the question you should be asking yourself is, if I have dynamically changing document collections, well, then I should probably not be thinking about batch approaches. I should be thinking about online and streaming optimization algorithms. And most of these, they're only going to require like one step of parameter state. That's easy to keep track of. No big deal. So just do that. And then you get additional payoffs because, you'll have instant, always up-to-date results. And really, the hard part is just putting the effort into learning a new class of algorithms. So, and this isn't specific to topic modeling. This, applies in, time series space. This is even something as simple as calculating variance can be done totally online, just keeping track of a handful of counts. And so that brings us to the end, and we can go through some questions now.
So before we start on the questions, a few credits. So Tommaso and Simone, they are the ones who came up with the algorithm I had showed for the JIRA, and we don't have a name for that yet. We don't know what to call it. It's not LDA, but yeah, it does compute topics on streams. And obviously some of the OpenNLP folks and Fabian, who has been very helpful. Yeah, questions, sorry.
Yeah, so one of the earlier slides where there was the architecture or the Flink job, you had a backward line. So
yeah.
How do you do that with the iteration API or?
So we're actually working over multiple windows. You're working over windows of data. So the first window, it's a cold start. When you start the job, it's a cold start. So you don't have so you kind of assume that's 0, the value is 0. So on the subsequent windows, you take the topic model it's stored as a state parameter. It's a stateful parameter. You take that from the state, and you calculate the new embeddings for that particular window. You take that. It's not iterative jobs. We're kind of doing it in a sequence in the regular workflow itself without using iterations. So you take this, and you take the one in the state, and you take the new embeddings, and then you calculate the average and update your state with that. So the next window again would take read the value from the state, the new value from the state, and calculate the embeddings, average that, and update state again. It's kind of like a Markov chain. So you just have the previous state. That's all you store. Any more questions? Patrick, you should have questions. This is more relevant to you, ResearchGate. Yeah. Yeah.
And another one. So you said that it could be done with broadcasted. So you are have the assumption that the model is not big that you can multiply it for the parallelism and every task. Okay.
Yeah, so there's generally correct assumption that these the topic matrix isn't typically that big. You're usually paring down the vocabulary in some way. So there's a couple of variants of this online LDA. One to make parallelism sort of cleaner, and the other one to support infinite vocabulary. So, the sort of the, algorithm that was laid out, if you looked at it closely, it doesn't directly do, vocabulary update, but it's, it's not difficult to do that. But since, this is not going to be, a giant amount of state, this is the kind of thing that's probably, less than a megabyte in size in most cases.
Okay, I think we're done with questions. I think let's give another round of applause to Suneel and Joey.
Thank you. Thank you.